All right, so yeah, I started the recording, so we can go ahead, or give me a second. Got one more thing to do, and then we'll be ready. All right, so we can start now. Well, thank you guys for coming to today's session. We're going to be talking about DC motors and how you can analyze them to predict how your robot's going to work, and then how to control them so that your robot works in a desirable way. So in case some of you guys don't know me, my name is Varun, and I'm a ECE master student right now, and I got my bachelor's in electrical engineering last year. And in the past, I've worn a lot of hats: robo racing electrical lead and electrical training lead. But now I don't do robo racing anymore. I'm on BattleBots, and I'm working on the BattleBot hockey. So the first thing, we have about 4 different ideas that we want to talk about today. We want to talk about how to write down the equations which describe a DC motor, and then how to get the relevant information out of a data sheet so that you can use that along with these equations in order to properly design a DC motor mechanism. Then we want to understand the circuits that you can use to control a DC motor. And then lastly, we're going to use a PID control in order to control a DC motor. So first, we're going to talk about the physical phenomena that take place inside a brushed motor and how they work. So you guys might remember from physics 2, in the presence of a magnetic field, if there's a current flowing through a wire in a magnetic field, there's going to be a force that's exerted on it. And you can point your fingers in the right-hand rule in order to determine what the direction of the force is. So these X's mean that the magnetic field goes into the page. So put your index finger in that direction. Your thumb goes down in the direction of current, and then your middle finger will be pointing to the right, which is the direction of the force. And then here you can also see a converse effect, same electromagnetic phenomena, but in this case, if there's a velocity of the wire moving in a magnetic field, the end result is that an electric potential will be applied across the wire. And here the velocity goes in this direction, and the end result is E, your electromotive force or electric potential, which is oriented up. And the same thing, right-hand rule applies here: index finger in the direction of the magnetic field, thumb in the direction of velocity, and then your middle finger will be in the direction of the electric potential. So now we can take that and we can apply that into a simple motor. So here's the cross section of our imaginary motor. So these are wire loops, and the wire is going to go into the page here, and it's going to come out of the page here. And when you give this a positive electric potential, and here you give it a negative, we can analyze at around this edge here, the magnetic field is pointing radially. It's pointing towards the center of the circle. And using your right-hand rule, you'll see that magnetic field radially, the motion is, the current is into the page, and then your thumb is now pointing in the direction of the rotation. So this is going to move perpendicular to that magnetic field. Since the magnetic field is always oriented towards the radius, the motor moves always perpendicular to the radius, which means it goes in a circle. The problem arises when the magnetic field around this part changes direction. Here it's pointing towards the radius, here it's pointing directly away from the radius. So we add this thing called a commutator, and the commutator is a sliding contact which switches the polarity. So you can imagine that once this wire has reached here, this wire has reached here, these little sliding points are going to switch to touching the other corresponding contact. So this means that the motor is going to change the polarity across the coil as you transition from having the motor in this direction to having the motor in this direction. So I briefly alluded to it, but here are the three main parts of a motor. You have the commutator, which is that sliding contact that I mentioned before. You have the stator, which is the magnetic field, or the permanent magnet which generates the magnetic field. And lastly, you have the rotor, which is the inner part, which has the coils wound around it. And this is the key feature of brushed DC motors, is that the permanent magnets are going to be on the, or a permanent magnet DC motor for particular, has the magnets mounted on the stator and the coils mounted on the rotor. And then the sliding contact creates the electrical connection between the stationary part, which is your wires, and then the moving part, which is the coils. And you can see that the motor is going to rotate, and then once it crosses over the commutator, the coils change polarity, and that causes it to continue to rotate. So based on those previously mentioned physical phenomena, we talked about how the current generates a force based in a particular magnetic field. And that when you talk about a rotating system, it becomes from a force to a torque. And in this case, the torque of the motor, tau, is related to some constant k times the current, so ki times I. And conversely, for a wire moving in a magnetic field, which is the case of the fact that the motor is spinning, the angular speed is related to the electric potential, so omega equals kV times E. And these two quantities, Ki and Kv, are based on the materials inside the motor. They're based on the magnetic field. They're based on the size of the motor. And they're actually both related to each other. Kv is just 1 over Ki. So now we're going to be talking about the equivalent circuit model of a DC motor. And this is really important. You guys should, commit this to memory, because every conclusion you want to draw about a DC motor, you can draw just by looking at the equivalent circuit model. So here we're just going to have all the variables labeled. VA is the applied voltage. This is you apply a particular voltage to the motor and then it causes it to spin. IA, or just I, is going to be the current that flows through the motor. It's the current drawn. And then we have the resistance, the inductance. Because the coils are made out of wires that are long, they have some resistance. And because the coils are wound up to hold magnetic fields, there's a inductive component. And then here, this is like basically a variable voltage source, which represents the EMF that's created by spinning the motor. So like I mentioned, that physical phenomenon here, if the motor is spinning, there will be a voltage across the coils, and that is represented by this component here. But then remember that a motor converts electrical energy to mechanical energy. So here's the mechanical side, where you have a shaft rotating with a certain angular velocity. And the shaft is connected to a mechanism with some inertia, J. So now let's actually try to do the circuit analysis for the motor here itself. So you guys can remember Kirchhoff's laws, right? The current flowing here, we can just analyze this loop and the voltage drops in terms of it. VA minus I times R minus the voltage drop across an inductor. Let's write the equation for that real quick. DI dt L equals V. This is just, physics 2 or circuit analysis course. You might remember this equation, but we're going to use the voltage drop across the inductor right here. DI dt times L. And then lastly, we want to subtract the back EMF across the motor, which, if you guys remember, is going to be omega equals kV times E. So here we want to solve for E, so we divide by kV, and then we get minus omega over kV. So this is the first equation. And then now we can write the equation for the mechanical side. You guys remember that torque equals angular momentum times the angular acceleration, which equals J times d omega dt. And then we also have another expression for torque, which is that torque equals Ki times I. So we can put these two together here and say, we want to solve for d omega dt. But let's just do, oops, J alpha equals Ki times I. Actually, if we want to be a bit more specific, we should note that the torque here, this is the net torque, which is actually going to be equal to the motor torque minus the load torque. And the load torque could be if you like had a weight attached to the, you could have a weight attached to the end of this motor as well. So now we can write the equations properly. Equals, we'll substitute Ki times I in for the motor torque, and you get Ki times I minus tau L. So now the important part is these are two differential equations. Let's put them in a good form by solving for the actual differential. And then you get di dt equals 1 over L times all of this other stuff here, VA minus RI minus omega over KV. And then we can do the same thing with the second equation here. Alpha is what we want to solve for. So alpha equals d omega dt, which equals 1 over j, the angular momentum, times ai times I minus tau load. And this is an unknown thing, or I guess it could be known once you've designed your mechanism, but for now, in the general case, we don't really know what tau L could be. But these two here are the two differential equations which basically describe the entire process of a DC motor. And you can see that repeated here with better handwriting than mine. I add a third differential equation here, d theta dt equals omega. This is just the definition of angular velocity as being the derivative of position. And depending on whether you want it, this equation might be of importance to you if you want to control the position of the motor rather than the speed. But either way, these are the critical ones, and then this is just your extra. So you generally need to get those parameters such as the resistance, the inductance, KV, etc. from the motor datasheet. But I know that a lot of times if we're not buying from a nice manufacturer like Maxon, we won't necessarily have the inductance. And inductance is also not very easy to measure, so sometimes we have to just ignore it in our model. So here we can assume, you can actually sometimes assume that the inductance is small, and then we redraw our circuit from before as the following. So here we just have the resistance. There's no inductive component. And then plus minus VA E. And then I'm not going to draw the other parts, the mechanical parts. But either way, this gets rid of the equation which has di dt in it. And you can directly calculate I as doing I equals VA minus omega over KV all over R. So now that we've talked about the physics behind a DC motor, we can talk about how to actually drive it. So you need some sort of circuit which controls the voltage across the motor because that's your input. And as you've probably noticed by now, in order to go in forward or backwards, you need to be able to switch the polarity in order to be positive or negative voltage. And so before we get into that, we can talk about what a MOSFET is. MOSFET is a metal oxide field effect transistor, and that forms the building block of power electronic circuits in general. And transistors basically act as electronic switches. So applying a voltage to the G, which is the gate of the transistor, will control the resistance between the D and the S. So by putting charge on the gate, giving it a voltage, you can make the resistance very low and thus allow you to conduct a lot of current through the transistor. So small voltage controls a large current, and this is really useful. Here is a way to control a motor where you can only go in a single direction. And we do this with just one transistor here. So you can think of if the gate has a voltage applied, the drain source resistance becomes very low, and so current is allowed to flow. The transistor it basically switches on. So then the VCC, the voltage or current travels from VCC through the motor and down through the transistor. And when you turn the transistor off, this becomes an open circuit, and current is no longer allowed to flow. One, I guess, thing to point out here is this diode D1, which is applied in parallel to the motor. And that's because you guys remember the motor has an inductive effect. And what this means is when it'll try to maintain the amount of current flowing. So even once you turn off the transistor and there's no current flowing through this path, the current needs an extra path or needs another path to flow in order to dissipate that energy. And so we add the diode in order to protect the transistor. Otherwise, the inductive effect will cause some large voltage spike right here, which tries to force current through the transistor even when it's turned off. So that lets us only control in one direction because there's no way of switching this plus terminal and this minus terminal here. However, in order to do bidirectional control, we can use a circuit called an H-bridge. And here, instead of one transistor, we have 4 transistors arranged like so. And there's 2 possible ways that current can flow. If you've turned on this transistor, and then turned off this and this, it basically acts as a circuit with a path that goes in this red path. So the positive voltage goes to the left side of the motor and comes out of the right side to ground. And conversely, if you turn off Q1 and Q4, turn on Q3 and Q2, the positive voltage then gets applied to the right side of the motor and the negative voltage gets applied to the left. So seeing this, you can actually have either a positive or a negative voltage across the transistor, and so it can spin in both, or excuse me, across the motor, and so it can spin in both directions. So we talked about spinning in both directions, but we get multi-directional rotation, but we didn't talk about the speed. And in order to control the speed, you need to be able to control the voltage finely. The way that we do that is through pulse width modulation. So even though the instantaneous power is just what it is, you can control the average power. And so you can see with 0%, 25%, 50%, or 75%, what changes is the duration of the pulse, which is high. So that you can kind of intuitively see that the more percentage of high there is, then the more power is transmitted into the motor. And what effectively happens is that the duty cycle, which is this percentage, multiplied it by the high voltage, in this case is 5 volts, and that gives you the average voltage, which is effectively what is given to the motor. And you might be thinking, oh, these pulses are just going to make the motor go fast and stop, go fast and stop. But remember that due to the inertia and due to the inductance, there's a smoothing effect which it causes it to average out. So now we're going to talk about some useful things you can use when you're designing a mechanism which has a DC motor. So first, we're going to give some definitions of useful terms, which is stall. Stall is when you apply power to the motor, but it's not rotating. So it's stuck due to some external torque. Stall torque is the particular torque required in order to cause it to stall. And usually the stall torque is given at the max voltage. So a motor that's rated for 12 volts, when you look at the stall torque of the motor, it's the stall torque when you have 12 volts applied across the motor. And then lastly, the free speed is the maximum speed of the motor with no load applied. So no torques no external torques, it'll just spin to its maximum speed at the maximum voltage. So when you're using a motor, the first thing you have to look at is the motor curve. And the motor curve is given for a particular voltage, which is usually the rated voltage. So this is a VEX motor, if you're familiar with VEX. And the rated voltage is like 7.4 volts or something. So this is what that relation looks like for 7.4 volts. So here the interesting things is that the speed is on the vertical axis, torque is on the horizontal axis, and the speed-torque relationship is linear. And this means that at a particular voltage, if there's a particular external torque on the motor, it's not going to rotate faster than that. And consistent with the equations that we talked about earlier, the torque and the current are linearly related. So the higher the torque, higher the current. And what this means is, if you guys remember the formula of power equals speed times torque, the end result is that you get your power output is a quadratic equation. And the maximum of this quadratic equation is what you want to design your mechanism for, so that your motor is putting out as much power as it can. Otherwise, if you're on the wrong side, you're going to be, you could have picked a smaller motor, essentially. You're wasting energy. And then lastly, we have the efficiency, which is given by this shape here. So usually the most efficient motor operates at around 15–20% of the max torque. So one useful thing we can do is we can figure out kV just by looking at this motor curve. And by figuring out kV, you figure out Ki, so on and so forth. So we look at the stall current, which in this case is 3.6 amps. And then at the stall condition, remember that the speed is 0. So the equivalent circuit model then becomes just a resistor between VA and ground. So here you can easily calculate, if you know the current flowing in here and you know the voltage, you can easily calculate the resistance. So given that you found R, you can now use this equation here to find kV. So just solve for kV and for any particular point along this line where you know I, R, omega, and V. So whenever you design a motor, the motor is going to spin at whatever speed it's designed for. And you, as the designer, you can make the choice between torque and speed on the output by adding gears or some machinery or some reduction. And if you want your motor to just apply the most amount of power that it possibly can, you need to make sure that the load torque is 0.5 times the stall torque. And you can do this just by adding a gear ratio so that the torque experienced by the motor is more or less. However, when you want to design precisely, and this is kind of like a rule of thumb, if you want to design so that your motor can move a heavy object precisely, you actually need a bit more torque than if you just want to make it go fast. So my recommendation is that your load torque should be no more than 20 to 25% of the stall torque. And this is something important if you're designing like a robot arm, for example. And now we're going to talk a little bit about electronic speed controllers. And they're just basically circuits that have all the important hardware, such as an H-bridge and maybe some other communication circuits, some sensors or whatever, built into one. And you can get a speed controller that's rated for a particular voltage and current. You want to obey those limits because the too much current flowing through a circuit or a ESC or circuit in general is going to lead to the overheating. So designing, you want to choose your ESC and design your mechanism in such a way that the current limit is not ever violated. And you can do this mechanically by adding a clutch or some sort of slipping with maybe a flat belt that slips on the pulley, which will limit the torque applied. You can also, if your ESC has a programmable feature, you can program a current limit into it so that it will shut down if it exceeds too much current. And just so that you don't, burn up your ESC because you stalled your motor. And that is the thing. You should usually be very careful when you design a motor for the case of stalling. And that's actually one of the reasons why you want your load torque to be 20 to 25%, is because for robot arms or like precise positioning applications, you might actually need to stall the motor at points because you need to hold something in a particular position. But the same ideas of like choosing ESC based on current, overheating, and using torque limiting applies both to brushed and brushless motors. And in fact, the math kind of works out really similarly for both of them. And so the last thing that we're going to talk about today is feedback control for motors. So in order to do feedback control, you need to have the controller needs to have some understanding of what the motor is doing. And in particular, we want to measure it using an encoder, which is a sensor that measures the speed or position of a motor. So here we have two different types of encoders. We have an incremental encoder and an absolute encoder. And they shine a light through these gaps or use some kind of sensor to detect these black sections. And those generate pulses of like electric pulses. So here, an absolute encoder has a different code for every angle that the disk can be at, whereas an incremental encoder just generates a pulse after you've rotated a certain amount. And you can measure the phase shift because you can see that this outer ring and the inner ring are offset slightly. You can measure that through a phase shift in order to determine whether the wheel is moving forward or backwards. So feedback control is improving the performance of the system or controlling the performance of a system by taking measurements of it. And like I mentioned earlier, the most common thing that we're going to want to take the measurement with is an encoder. Because generally, if you want to control the speed of the robot, you're going to need to measure the speed of the robot. So an encoder is a good choice for that. So here is an example of a control loop with a feedback. So you give the goal speed, R, to a PID controller, which I'll explain what it is in a second. But the PID controller takes the input of the speed and outputs the predicted voltage. And then the voltage is applied to the motor. The motor then exerts a torque on the mechanism, which could be like your robot's drivetrain, for example. And then the mechanism causes something to happen in the real world, which changes the state of the system. And the state is like the position, velocity, current, etc. And then lastly, an encoder, which is our sensor in this case, will measure that and then give you a measurement of the velocity. And this measurement of the velocity through this line gets fed back into the PID controller. So this is what we mean by feedback. So first we start by talking about proportional control. So we guess like, okay, why don't we just make the speed proportional to the error? And in this case, error is the difference between where we want to be and where we are. And then we simply multiply that by a constant and make that our voltage. So as long as Kp is positive, you can kind of tune this, making Kp large will cause it to correct really hard. It'll apply a large voltage when there's some deviation. If Kp is small, the voltage applied is just very small in terms of the error. And another option we could try is we can try proportional and integral control, which is when proportional control on its own can get stuck. And I'll give you an example of that. You could find an equilibrium point just like where it ends up managing, the math works out perfectly that the amount of torque you're exerting is just not enough to send you to the next, or send you forward, so you get stuck. So proportional integral control, we add up some of the sum of all the previous errors, and then we store that in something called a variable called sigma. And now we add u equals to kp times the error plus ki times sigma. So this represents the current error, and this represents if there is a history of error in the past. And lastly, we have proportional derivative control. So we talked about having this extra force to push the robot forward, but the opposite could be a problem, which is that the robot is moving too fast. It has momentum, and it's gonna cross over the goal without slowing down in time. And here, the derivative term is gonna be the current error minus the previous error, which is kind of like a difference equation, sort of like a differential equation. But we use both the error and the derivative of the error. So that way, if the error is decreasing very fast, this is going to be a negative number, and it's going to slow down the amount of, it's going to decrease overall the power that's being applied. So you can combine P, PI, PID, PD, any combination of those. Generally, you want to have proportional control, but you can add integral or derivative control as you want. And the integral term, like I mentioned, it has it basically adds an extra inertia effect, and the derivative adds an extra damping effect. So integral adds energy and derivative removes energy. So here's a step response, which means you command the system to go from 0 to 1, and you watch to see how it reaches that. And this is a good response. You can see that the robot rises, or the position of the robot rises and reaches the goal. And this is overshoot. So in here, the robot will pass over the goal and then have to adjust back and forth. And overshooting leads to some oscillation. Over time, it may settle down, but it'll bounce back and forth. And this is something that happens when your gain is too high, like your proportional gain might be too high, or your integral gain might be too much. And those are that's the gains I mean are referring to those constants Kp and Ki. If those are too much, you might end up overshooting because you're adding too much energy into the system. And then on the opposite, you can have steady state error, which means that the robot will stop before it reaches the goal. So here it stops at 0.91, but it's trying to get to 1. And in this case, the issue is caused by a lack of energy. And the only way to solve that is to add more energy, such as integral or adding more proportional gain. So in practice, there's some things that you have to care about. For example, the control limits. Sometimes your PID controller, if you're really far away from the goal, it could output some value that's really large. So you have to be careful that your PID control is really only operating between your voltage limits, right? Because you can't give more voltage than your battery has. So there is naturally a limit imposed on how much power you can give to your motor. And what this means is if your motor can run at max of 900 RPM, you can't expect the motor to be controlled well at 900 RPM. That's because there's no wiggle room. Let's say that if there was some extra load on the motor, it just wouldn't be able to add more. If there was some extra load on the motor, it wouldn't be able to add any more power to compensate for that. It would just be stuck at whatever the maximum voltage allows it to spin at. So when you use your motor, you have to make sure that you're only commanding it something that's like well within its capability to allow for that wiggle room. And then another problem that you might encounter is integral windup. And in integral windup, the integrator, that value of sigma, it grows too large and it becomes overpowering. And for example, the integrator will want the motor to go faster to apply more power. But if you reach that control limit, for example, you can only run 12 volts on the motor, and the integrator is going to cause it to keep going up and up, even though it's already applying 12 volts. So in order to avoid that, when you program a PID controller, you have to make sure that the integral is limited. You can either limit the value of sigma, or you can only integrate when you have that wiggle room. So whenever you make a PID controller, you have to actually tune it in order to get the desired behavior. And tuning means that you have to choose those gains, Kp, Ki, and Kd, properly in order to have the system reach its goal. So here we have some common behaviors, like if your robot or mechanism or whatever is getting stuck before it reaches the goal, that's steady state error. And if there's steady state error, you have to add an integral control. So if you were using PD in this case, you would have to use PID. Or if you were just using P, you would have to use PI. If your robot is moving too fast or it's overshooting, you need to decrease the P and I gains. And like I mentioned, the P and I gains add energy, and the D gain removes energy. The robot is moving too slow. Like I said, you want to add more energy, so you have to increase the gain. And then in order to solve overshooting and oscillation, you can also, in addition to decreasing the energy, you can also increase the derivative gain. And this has a dampening effect, so it'll slow down those oscillations. And the last thing we're going to be talking about before we go from lecture to practice is we're going to talk about simulating the motors. And I don't know if any of you guys have taken like a numerical methods class or something like that, but what we're basically going to be doing is solving the differential equations using a numerical algorithm. So I hope you guys all remember what a Taylor series is, but here's a refresher. It lets you approximate an arbitrary function. As long as it's differentiable, you can approximate it with a polynomial. So in this case, f of x plus delta x is going to be equal to this expression here, f of x plus delta x f prime of x. So it's a combination of the function value, the derivative moved over by a little bit, the second derivative, the acceleration, moved over by a little bit and multiplied by a weighting factor, and then this continues on for infinity. So here now, in order to solve a differential equation, you remember in the general form we have x dot, or the derivative of x with respect to time is some function of x. And we want to find the function in terms of time, which is the trajectory. So here we use a Taylor series approximation. And the Taylor series approximation, we want to find this, we take only these two terms. And we say x of t plus delta t is going to be equal to the function plus the change in time times the time derivative. And this is something that's given to us. We pick this in our program, and then at every point in time, we record the last known value of x of t. So by doing this, you can kind of step one at a time through points in time, and then you can calculate the trajectory. So that's it for the talking component. I do have some programming aspects that I've put together, and I'll send a link to that in the chat. If you go to, actually, quick show of hands, how many of you guys have MATLAB installed on your computer right now? All right, cool. So you guys can actually do this begrudgingly. So here I have some sample code that I wrote in MATLAB. There's a practice for DC motor sim and DC motor sim PID. The goal of this practice is that in DC motor sim, you take the DC motor equations and then you put them into the program, and then you should be able to simulate the motor and watch the state variables of speed, position, speed, and current. You should be able to watch them evolve. And then once you've done that in the PID version, you then can also program a PID controller in, and then tune that PID controller in order to, make it do what you want. So I guess for now, I'm going to stay on the call, and I'm going to actually stop sharing this screen and start sharing my MATLAB, and then we can kind of go through it. You guys can also feel free to go at your own pace. But, oh yeah, maybe I should jump back to the equations, and then you guys can look at them when you try to write the program.